let's start the last.
Welcome back, everyone. It's my pleasure to be here on day 3. I'm going to share my screen and we'll just dive right in. So let's share. There we go. Share that. All right. Day 3, October 8th. All right. So as advertised, today we're going to talk mostly about the idea of whether for a given topological space we expect the shadowing property. So we'll just dive on here. So, for the sake of completion, here's our definitions. An orbit is the sequence where you just iterate the function f on a single point. A pseudo-orbit is like that, except we take a sequence and the point-wise difference between f of xi and xi plus 1 is bounded by epsilon. We say that f has shadowing if every epsilon has a delta such that every delta pseudo-orbit is epsilon shadowed. All right, so this is the stuff we've been working with for 2 days. All right, so before we get into the topic today, this was brought up yesterday, and I just wanted to make this a bit more formal. Okay, the notion of how shadowing relates to perturbing a map. So if f and g are 2 maps, so that at each point x, the distance between f of x and g of x is small, then a orbit for the function g is actually a pseudo-orbit for the function f. All right, so if we have shadowing, then the orbits for the function g, if g is a function that's near f, the orbits for the function g are well approximated by orbits for the function f. And that's because the orbits for the function g are pseudo-orbits for f. And so this relates to the various notions of stability. We talked about that briefly yesterday, but I just wanted to bring this up and make it a bit more formal here. So to the topic at hand today. So there's sort of 2 big questions we'd love to be able to answer regarding shadowing. And the first is, given a map from a space X to itself, can we determine whether that map exhibits shadowing? And the answer to that question is yes, sort of, kind of, under appropriate circumstances. That is a difficult question. We have complete characterizations thanks to the theorem of Walters for X being shift space, or subshift rather. The work of Covington and York, they've completely characterized when a tent map has the shadowing property in terms of the needing sequence of the critical point. That's a very technical result, difficult to check. And beyond that, there's not a lot there. There's a lot of ad hoc sort of methods that you can use to, given a map, determine if it has shadowing, but characterizations are few and far between. So the question I'd like to address today is a little bit different. So rather than given a map, can I determine if it has shadowing? Let's talk about this. Given a space, should we expect a map to have shadowing? So the question we're going to address here is, given a space X, a metric space, are maps with the shadowing property common in the sense of topology or uncommon in the sense of topology? And when we say common, when we say generic, that's not working. Sorry. There we go. Okay. So when I say common here, what I'm meaning is that there is the set of maps F with shadowing contains a dense G delta set. Okay. So let's recall really quick, a set is dense. So in order to really talk about this, we need to have a topology on the space of function. We'll talk about that in a second. And we're going to want to argue that we're going to know whether the set of functions with shadowing is dense, which is to say that in any neighborhood of points, any neighborhood of functions, there's at least one map with shadowing in it. And we want it to contain a dense G delta set. Now, a G delta set is the standard nomenclature for a countable intersection of open sets. Okay. So in a very topological sense, most functions will have shadowing if there's a dense G delta set of functions with shadowing. All right, so that's our goal, and we're going to answer this question for a couple of classes of spaces X. Okay. So we're going to focus on question 2. So let's define what we mean by the topology on the space of continuous functions. Okay. So for a compact metric space X with metric D, the space of continuous self-maps is the space I denote it by script CX. Okay? And we equip it with just the max or the sup metric, right? It's a compact space, so we can put max there instead of sup. What's this? The supremum overall pairwise distances. We look at a point X, we see where F takes it, where G takes it, we compute that distance, we do that over all X, take the supremum or the maximum, and that's what we call rho. So there are many important subspaces of C of X. These include the space of homeomorphisms, which we call H of X, the space S, which consists of surjections. And if X had enough structure, we could even talk about the subspaces of different diffeomorphisms or n times differentiable maps. But for the purposes of today, we are not going to talk about that. We're not interested in the analysis today. We're going to focus on C and S. And to a lesser extent, we'll talk about H. Okay, so we're going to talk about the space of continuous functions, the space of surjections, continuous surjections, and the space of homeomorphisms. All right, they all have this same metric attached to them. All right, so a brief history of this problem, well, a brief history of shadowing, really. This sort of study of the shadowing property really started back in the 60s and 70s with the work of Anosov and Bowen, where they were looking at various diffeomorphisms, and they had this category of diffeomorphisms called axiom A. It was really the start of the study of shadowing, or the pseudo-orbit tracing property. All right. Shortly after that, and I say shortly, 12 years, Yano, I can't remember the first name there, demonstrated that shadowing is a generic property in the class of homeomorphisms on the unit circle. Right, so we're looking at the unit circle, we're looking at homeomorphisms. We know a lot about homeomorphisms of the unit circle, and Yano demonstrated that shadowing is an expected property among those homeomorphisms. Now we saw 2 days ago that there are lots of homeomorphisms that don't have shadowing, right? Any rotation does not have shadowing, okay? But rotations are not most of the homeomorphisms. The rotations are a very thin subset of the homeomorphisms of the circle. All right. After this, O'Donnell in 1990 extended this result to smooth manifolds of dimension at most 3. So that's a big step up. And we know that dimension 3 is a big step in the world of manifolds. After this, Mizera showed that the shadowing property is generic in the continuous maps on the interval and the continuous maps on the circle. So this is a bigger result than the result for the homeomorphisms, although the homeomorphism case is a little bit more complicated and it's less of a, anyways. In 1999, more recently, Pilyugin and Plamenevskaya, they demonstrated that shadowing is generic in the class of homeomorphisms on manifold M, where M is sufficiently nice. I don't remember the exact criteria there. But there was a small, very modest list of conditions they needed for that manifold. The dimension was not one of them. Okay. In 2013, Mazer and Okroha, they demonstrated that shadowing is generic in the space of continuous functions and the space of surjections for any compact manifold M. Okay. And that's where sort of myself and a few of my colleagues have sort of stepped in here to take where we're going. So these results, the proofs are all very interesting. The proof of this last result here, we'll sort of talk about that as we go. In fact, the results and proofs that I'm going to talk about today are very much going to be mirrors or analogs of the arguments in that paper. So the goal today is to sort of extend this class of things that we expect shadowing on. Right, so we expect shadowing on manifolds. We expect shadowing on closed manifolds, compact manifolds. Question that sort of drove this is, can we extend these results to branched manifolds? Now, branched manifolds are a very, very big class of things. You have to worry about how they're branched, how those ramifications match up. And sorry, what we're going to do is we're going to focus on the one-dimensional case. So a natural place to begin this extension is to generalize those one-dimensional results. So we had these results concerning the interval and the circle. And what we're going to do today, and we're going to push a little beyond what's said here, we're going to try to extend these results to trees, or more generally to something called a dendrite. So a tree here, there are lots of things that you might call trees. These are going to be just finite acyclic graphs. Okay, so graphs with no loops. So something like this. Okay, trees. All right, now dendrites, let's talk about dendrites. Dendrites are a natural generalization of trees that arise in a number of contexts. And if you've had a course on continuum theory, you've seen these, but for those of us who maybe aren't super familiar with them, a dendrite is by definition, well, by definition, a dendrite is a lot of things, but equivalent to most definitions, a dendrite is a compact, so we're dealing with compact, locally connected metric space that is uniquely arcwise connected. And if we think about trees, this is exactly what trees are. Trees have the property that given any 2 points, given X and Y in a tree, there is a unique arc with endpoints X and Y. Okay. And so locally connected then, let's just remember this. This means that for all X in T, there exists a neighborhood of X with N connected. Okay. And so these are what dendrites are. They're the natural extension, they're natural generalization of trees. You can often think about them as infinite trees or trees with infinitely many branch points, provided we don't break this locally connected condition. Okay. So the next few slides, I have a couple of examples of dendrites. Oh, the metric, right. Before we get too far, one of the great things about dendrites is that they can be equipped with what's called a taxicab metric. So there's a natural topology that arises on these dendrites, but we can always show that it's equivalent to this, what's called a taxicab metric. A taxicab metric is just a metric that measures things by the length of the path between them. Right? Instead of the triangle inequality, we have the triangle equality. Right? So if I have a point X, a point Z, and a point Y, the distance between X and Y is exactly equal to the distance between X and Z, plus the distance from Y to Z, right? Because in a dendrite, it's uniquely arcwise connected. So to get from X to Y, I have to do this, and then I have to do that. All right, so as promised, a few examples. Oh, sorry, we're not there yet. I'm getting things out of order. Dendrites naturally have sort of 3 categories of points. 2 of them are sort of worth talking about. And these are the endpoints. Okay, an endpoint of a dendrite is a point such that the dendrite D, removing that point, is still connected. It's a non-separating point. This is the natural notion of an endpoint of a graph. It's the exact same definition. We have branch points, or sometimes called ramification points. These are places that if I remove that point X, I have more than 2 components. And then I have all the other points, okay? So if I had a dendrite that looked maybe something like this, then we could pick out the endpoints as here, 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 and my branch point here, and exactly the places you expect. They're very easy to identify visually. All right. Among dendrites, it is most common in the class of dendrites that both endpoints and branch points are generically dense. So this picture I drew here, where the endpoints and the branch points are sort of sparse, is sort of the least frequent way that dendrites arise. It's more common that the branch points are essentially everywhere and that the endpoints are essentially everywhere. All right, so let's look at some examples of dendrites. Let's start with the most boring dendrite. A lot of authors exclude this, the point. It's locally connected, it's uniquely arcwise connected, it's compact, it's metric, it's boring. All right, arcs. Of course, this satisfies all the same thing. That's the second most boring dendrite. You might have something like this. This is supposed to be evocative of the binary tree, where you have, say, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and then you keep going up. And then the points up here at the top, if you've angled these correctly, we have that this is going to be acyclic, it's going to be uniquely arcwise connected, and the points at the top are just infinite binary strings. So this is an example, and here we see that the branch points for this dendrite are also very sparse, right? We have this unique branch point. You have actually not branch point, so forget that one. But here's a branch point, and it's nowhere near any other branch point. Here's a branch point, nowhere near any other branch point. And the endpoints are all locally just up here. So we have whole swaths of the space with no endpoints. So a more typical example of a dendrite is something like this. Now this is a model of something that looks a lot like a Julia set. If you're familiar with complex dynamics, this is a fractal. Right? There's a lot of self-similarity here. Right? If you took this region here, blew it up, you'd have something that was basically the whole space. So we have here an example of what we might call a self-similar dendrite. And of course, we can only ever hope to draw a finite approximation of something like this, but we can see that intended here is that the branch points are in fact everywhere, and the endpoints are also dense. All right, so those are some examples of dendrites. And so, at least for the first part here, what I'd like to talk about is I'd like to work through a sketch of a proof that shadowing is a generic property in the class of dendrites. So this is a paper that myself, colleagues Will Bryan and Brian Rains worked on a few years back, where we demonstrated that if D is a dendrite, then the shadowing is a generic property in the space of continuous self-maps on a dendrite. All right, so the next portion of today's talk, we're going to walk through a sketch of this proof, some pictures, we're going to talk about some things. We're not going to write anything down super duper carefully because I think it's not really conducive to the medium we're talking about, but we're going to give a really great sketch of how this is done. All right, so in order to start, we first have this lemma. Okay, so the lemma says that if I take some finitely many arcs, pairwise disjoint arcs in a dendrite D, such that no endpoint of AI is an endpoint of D, then I can map an interval into D and find a delta greater than 0, such that F of that interval contains each AI, and any map G which is sufficiently close to F also contains all of those AIs. All right. So the idea here, let me draw a picture real quick before we go on. We have the interval over here. Okay. We have our dendrite over here. It does something wacky. Okay. And then we have some finitely many arcs sitting inside of it here, here, and here. Okay. And the idea behind the proof is that if we can sort of pick out a certain number of points to make sure to hit, let's make sure we hit this point, this point, this point, this point, and this point. And then if I map some corresponding points over here to those places, so this one maps to there, that one maps there, this one maps there, that one maps there, so on and so forth, then this will be a continuous map. Its image will contain all those green arcs. And if I have a map G, which is close to F, then the image of these blue points will be pretty close, okay? And will still be forced by unique arcwise connectedness to cover the green arcs. All right, so that's the picture we want to draw. All right, so since no endpoint of AI is an endpoint of D, we can find a sequence of points, Q0 through QK, in D, take out the union of those arcs, such that for each I less than or equal to K, AI is a subset of the arc between consecutive points there. Okay? So we can define then I, F, from the interval to the dendrite so that F of various points along that interval hit each of these QI, and then I say extend linearly between these places. Okay. Well, extending linearly, this is in the sense of the taxicab metric with respect to the taxicab metric. right? So basically we take the ith one of these units, we're dividing this into intervals of size 1 over k plus 1. So we're taking that interval of size 1 over k plus 1 and we're stretching it over the arc from qi to qi plus 1, however long that might be. Okay, and then we just are going to take delta to be the minimum of those distances from qj to uai. Okay, so here again, a slightly better picture of what I sketched earlier. Here's a handful of arcs in a dendrite. Okay, there are my points I'm going to try to point. Those are my anchor points. And then I'm going to define f from I. So let me draw this in here. So we have I. Okay, we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 anchor points to hit. And then I'm going to define my map so that this point goes to there, this point goes there, that point goes there, this point goes here, and that point goes there. Okay. In such a way that it covers, like this. So that's the green now indicates the image of f of I. Okay. Now, because of the way we've done this, if G is nearby to, so the green indicates F. If green is nearby, let's do this in black, then this point here maps into the delta ball around that point. This point maps into the delta ball around that point. This point maps into the delta ball around that point. This one maps into the delta ball around that point. And this one maps into the delta ball around that point. And so by unique arcwise connectivity, the path from this to here, so let's call this one, let's call this I sub 4. Okay. I sub 4 under the black one has to map to some arc from this open disk to this open disk. And by unique arcwise connectedness, it must cover A4. Okay. So we're building up this skeleton. So that's a lemma that we're going to use here. All right, so our immediate goal in proving that the space of continuous functions with shadowing is generic in the space of continuous self-maps of the dendrite is to demonstrate that given a map F, given any continuous map F from the dendrite to itself, and any epsilon greater than 0, we can find another map G, which is sufficiently close to rho, within epsilon of F, that exhibits a sort of limited form of shadowing that is robust under further perturbation, right? So we're going to start with F, sitting in our space of CD, okay? We're going to take an epsilon greater than 0. Okay. Somewhere in this epsilon ball, we're going to find this thing G, such that under further perturbation, everything in this region, these things are sort of nice maps. These are the maps we want. Okay. Those are going to be maps that all exhibit some limited form of shadowing. Okay. And because of that, we're going to get that the set of maps that exhibit a limited form of shadowing, okay, is going to be dense, right? Given any F and M any epsilon, we can find such a thing. It's going to be open because we have a whole open neighborhood around it that does nice things. And that's going to be our way forward to get a dense G delta worth of maps that have shadowing. All right, so towards that end, let's fix an F from X, and that should be D to D, and fix a positive number epsilon. Okay. And what we're going to do is we're going to appeal to the existence of certain relatively nice coverings to get us where we need to go. All right, so we're going to choose an open cover of D by connected sets such that the diameter of each set is less than epsilon over 8, and the diameter of the image of each set is less than epsilon over 8. Since we're locally connected, we can certainly find a collection of open sets that cover D that satisfy this whole thing here. And we can do that with connected sets. And then compactness means that we can reduce to a finite collection. So we can find a finite collection of connected open sets, each of which has diameter less than epsilon over 8 and whose image has diameter less than epsilon over 8. Now, for each I less than or equal to n, we're going to define a map phi, which is, I call the pattern of the map. right? So we have some collection of open sets U, okay, something like this, okay, and just we have, let's draw another copy of that over here, right? And then if I think about the dynamics of the map, this guy right here, it maps, you know, we have some dendrite in here, it maps to some subset of this, right? So if this was, say, U2, then U2 would map into all of these, okay? And then that's what we mean by the pattern. We throw closures on there to deal with some edge cases, okay? So phi of I is the set of all indices, J, such that the image of U closure meets UJ closure, okay? Now, from there, we'd like to do, let's see, this is an older version of this. That is really frustrating. Sorry, okay, we're fine. Okay, so let me ground myself here again. Okay, so let's come back to these thoughts in a little bit. Okay, and we'll skip that for a minute. Okay, so far we know that X is locally connected and F is uniformly continuous, so we can accomplish this first stuff, no problem. Again, let's ignore that bottom stuff. That phi is well defined, that's just automatic. That's how I arrange this. Okay, I apologize. Okay, so let's talk through these. My apologies. We'd like to be able to find in each UI a tree SI that are all pairwise disjoint from one another, and subarcs of those trees, which are also pairwise disjoint in sufficient number matching the cardinality of the pattern. Okay? And then we're going to define a map G, which sort of acts on those. But in order to do that, we need to actually have a nicer cover than I've indicated. In order to make sure that these trees SI are pairwise disjoint, I need to know that these UIs don't overlap too much, right? If I have a situation where, say, I have a sort of a, what I call a dumb cover, where here's U, say, 2, but then U1 is this, and then U3 is this, then I have no chance of being able to find a tree in U2 that isn't necessarily interacting with things in U1 and U3. Fortunately, we cover. So the cover I want is actually what we call taut, which means that the intersection of the closures of elements of the cover meet, rather the closures of elements meet if and only if the elements actually meet. So we don't have situations where we have two things that kind of just touch but don't actually intersect. This is not allowed. Okay. We don't have that. And when I say the nerve of this is a tree, the nerve of a cover is the graph. So this is, here's the graph with vertexes U1 out through UN. So the vertexes are the open sets, and an edge, rather a face, put it this way, and faces, so this might actually be a polyhedron, U, let's see, dot U dot dot U dot dot dot, if the intersection of, let's do this, UI1, I2 out through IN, if the intersection of the UI, K equals 1 to N is not empty. So that's a little bit messy, but the idea here is that if I had a situation, let's talk about this up here. If I had a cover where I had a situation where I had something like this. So let's call this one U1, U2, U3, maybe we have U4, U5, U6. Then my nerve here has vertices U1, U2, U3, U4, U5, and U6. Okay. And then I have an edge or a face if there's a common intersection. Okay, so I'd have an edge from U4 to U1 because there's an intersection. I'd have an edge from U5 to U2 because there's an intersection. I have an edge here, I have an edge here, an edge here, and an edge here. And I'd actually fill this whole thing in. Okay. because this common intersection here. So this is not a tree because we have a two-dimensional cell in there. And even if we didn't have that intersection there, this would not be a tree because it has a cycle. Okay. So I want a cover which is taut and whose nerve is a tree. And I want those things to be locally, I want those sets to be connected. So we have to combine all of these things together. And if you've read through Nadler's continuum theory book, we know that taut covers exist for chainable continua essentially automatically. It's less clear for a wider variety of spaces. So how do we know that there is such a taut cover? Well, what we're going to take advantage of the fact is that a dendrite has dense subgraphs, subtrees, right? I know that given any 2 points in a dendrite, there's an arc connecting them. And given a sufficiently large collection of points, I can find a graph that is suitably dense. So maybe my dendrite is something like this, okay, where I have a lot of these, and then I have a lot of little small branches coming off. Okay. Well, for a fixed epsilon, okay, if we're wanting to find a small cover for any, let's call it delta, I can find a tree in here that covers all of the sort of large bits and ignores the small pieces. Something like this, okay? So we find a sufficiently dense subtree so that no point in the dendrite that's not in that tree is more than, say, delta away from that tree. Okay? Well, because this is a finite tree, we actually can definitely find a taut cover of that finite tree. Okay, that's easy to do. We just write one down. It's a finite graph. We can do it. Okay, we'll just put a few there, and we'll come along this way. Okay, so we have a cover of the tree. Okay. Now, because of the niceness of the taxicab metric and the unique workwise connectivity of this, any point that wasn't on the red tree has a unique point that's closest to it on the tree, right? This point right here, its unique point that's closest to it is right there. And this one here, its unique point is right there. So there's a nice map, let's call it pi, from D to G, and we'll call it the closest point map. Okay. And because the dendrite is so nicely well behaved, if we've chosen this G large enough, then pi inverse of one of these open sets here is connected and has small diameter. And it's absolutely crucial that we have things like local connectivity and unique arcwise connectedness to make that work. Without those two properties, this construction here doesn't quite work. All right, so we have such a cover, and because we have such a cover, we can from there prove that the core of each element is non-empty. So the core here is, we have UI, and then we have all of the other ones that might intersect it. Now these other ones, because the nerve is a tree, they don't touch each other, okay? And that because the green ones, the other ones cannot touch each other, that means that there's definitely some space in here. And this is what we call the core. So the core is a non-empty open subset of UI, which is sort of essentially intrinsic to UI. Now, UI is the only element of my cover that covers those things. And because it's an open set, I can find a tree in that open set. And when I say tree, an arc is a perfectly fine tree. So I can find SI buried in there. Okay, so we choose SI to be a subset of the core, and we choose it so that it doesn't, actually the endpoints of SI are not endpoints of D. That's easy enough to do. Okay. And then we're just going to choose an appropriately large family of subarcs of SI so that no endpoint of Tij is an endpoint of D or of SI, and so the Tij are pairwise disjoint. All right, so I have a picture of this on the next slide. All right, so here's a picture of a dendrite with a cover indicated by the light gray open sets. Okay, we see that the open sets are connected. We see that the nerve of the cover of open sets is a graph, right? No three are have common intersection. If I focus on this one right here, let's call this one UI. Okay. Maybe that one maps into these ones. Okay. And so this would be, this right here is the collection, so this is UI, and this is all of the UJ with J in phi of I. Okay. So this red thing here, it maps into sort of something like this. Who knows, but it does something like that. Okay. All right, so the idea here is that we take a tree in our core, so this is SI, okay. And inside of SI we find, so we have SI in red, and in green we have TJI, TJ prime I, and all of these other ones here, however many there were, right? Because according to this picture at least, there were four indices in phi I. So I need to pick out 4 arcs inside of SI. And what I'm going to do is I'm going to do that for all of them. So I'm going to find this tree SI in all of them and the TI is subsets of each of them. Excuse me. And what I'm going to do is I'm going to take the dendrite, subdendrite, SI star is going to be the subdendrite of D consisting of SI along with some additional pieces of the dendrite. Okay, so there might be some pieces of the dendrite that are sort of hanging off here sort of helplessly, and we're going to sort of build those in. Okay, so those are also going to be part of the dendrite there. All right, and then what we're going to do is we're going to, because of the way we've sort of isolated everything out, what we're going to do is we're going to redefine F on these SI stars in such a way that F doesn't change outside of the FI stars. So we're going to change F only on these trees SI star and the accompanying hanging bits. All right, so using our lemma that we talked about ages ago, we're going to map each of these subarcs Tij across each Sj that's in the pattern, right? So Tij is a subset of Si, and J is in the pattern of phi of I. And so I know that F of UI contains Sj, and we're going to map Tij so that it maps across all of those. Okay, so the picture is something like this. So we're going to take each of these things, each of these green arcs, these Tijs, and we're going to map them across the entirety of the red things, right? So each of these things, each and every one of these, I'm going to map so that it covers this, 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 and this. And that's what our lemma let us do. And it let us do it in a way that was sort of stable under further perturbation. Okay? So in order to finish defining the map on SI star, I need to define it elsewhere. Well, what we're going to do is we're going to take the, we're going to define our map on the endpoint here to be just g of x is going to be equal to f of x outside of these things. So everywhere outside of these red things, we're going to just take g to be equal to f. Okay? And then on these little green areas, the light green areas, we've defined what g should be. It's this map that stretches it across everything. Okay? And then between them, we're going to use this linear extension notion. Okay. So that's the idea there. And this is our desired map G. Now, in step 3, we were going to map them across each Tij so that the image was contained in that union. If we look at the details of that lemma, we can actually make it so that not only do they cover each of those Sjs, they cover each of those Sjs with some extra, right? So I have, you know, like maybe here's S1, here's S2, then my Tij maps across it in such a way that we have these anchor points. Okay? And these anchor points are sort of sequestered away from my S's so that if I take a map H, which is close to G, then it doesn't move these very far. Okay? And I'm still going to cover those S's. Okay? So if we choose this carefully, any H which is near enough to G will still do exactly this. Will map T, I, J across SJ. Okay. All right, so that's this slide here. We take that delta from the lemma, and then any map H which is within delta of G, we still have this same property here. All right. And so because of this, we can actually choose delta greater than 0 such that if xt is a delta pseudo-orbit for H, so we're perturbing H a little bit more, we still have that if xt belongs to ui, then xt plus 1 belongs to the union of the uj in the pattern. Okay, and that follows from the fact that H is sufficiently close to F. All right, so we built this map G that takes each of these little arcs, maps them across appropriate trees. Okay, we have the property that if H is sufficiently close to G, it still does that. And the pseudo-orbits for H follow the pattern indicated by phi. Okay, and what this does is it reduces pseudo-orbits for H to be patterns through the map phi. Right, phi is a connectivity thing. It takes the indices 1 through k, spits out a subset of the indices 1 through k. And so for any path through the set, so essentially what we're doing here is we're associating paths in 1 through k to the omega, and we're associating them, rather we're doing this, we're taking pseudo-orbits, and we're associating them with paths there, which are consistent with phi. Right, now phi is just a function. It takes a single index, spits out a set of indices. It's not a function, it's a relation. But it's only one step. Okay? So if we're thinking back a couple of days, this set of indices with this pattern is actually a subshift of finite type. So what we're doing here is we're taking delta pseudo-orbits for H. This is for H. And they're each associated with an element of a shift of finite type. Okay? And because shifts of finite type have shadowing, that means that there is an orbit for this map which witnesses that pattern, and we can construct our point from there. Okay, so given a pseudo-orbit, delta pseudo-orbit xt of H, its pattern through the cover is consistent with the relation phi. Okay, for each t, let's let uit be the element of the cover such that xy belongs to uit. Okay? By the construction of H, this nested intersection is non-empty. Right? We take SIT, we pull it back. This is the tree. Right? SIT is covered by TJI. So SIT pulled back contains that tree T, okay, which is a subset of S. And we keep pulling this back, and any point in this intersection will epsilon shadow the pseudo-orbit. All right, so any pseudo-orbit for T will be epsilon shadowed. Now this epsilon here is fixed. It was fixed up front. All right, so this was fixed a long time ago. It was fixed before we took our cover U and defined phi. Okay, so this epsilon here is fixed. But what we've shown now is that for all epsilon and any function in the continuous self-maps of D, there's a delta such that if G is with an epsilon of F, so we have F down here, we have epsilon, okay, then there's a map G and a delta such that if H is anything in here, then H has the property that every delta pseudo-orbit of H is epsilon shadowed by an orbit of H. Okay, so that's kind of shadowing. What we need is that for every epsilon, there's a delta. This is saying for this map H, for this epsilon, there's a delta. All right, so here now we can prove our theorem. Okay, the theorem is that if day is a dendrite, then the shadowing is generic in the continuous self-maps. All right, and the proof is a fairly straightforward thing. So for each n in the natural numbers, let's let script Rn denote the family of maps G that witness this almost shadowing property for epsilon is 1 over n. Okay. So Rn consists of all of those maps such that there is a delta, such that every delta pseudo-orbit is 1 over n shadowed. what we just proved is that, well, okay, sorry, back up step. By definition, Rn is open. We can actually see this nice and easily because Rn is the family of maps G, sorry, I misspoke. Rn is the family of maps G such that there is a delta greater than 0 such that maps near G have this property. Okay, and so by definition, it's open, right? G is in there only if all maps nearby have it. Well, and that means that if G is in it, that means there's this delta such that anything in there has it. Well, if I take anything in there that has it, I can just take a smaller delta, and that's contained in that ball. Okay, so Rn is open. By the previous theorem, Rn is dense. And that was this result back here that we were working through here. Okay, and so Rn is dense and open, and I intersect this, arranging over the natural numbers. Anything in that intersection has the property that for any n, there's a delta, such that every delta pseudo is 1 over n shadowed. Since 1 over n is tending towards 0, we actually get that for any map in this intersection, for any epsilon, there's a delta, such that every delta pseudo is epsilon shadowed. Okay, and so this right here, that is our dense G delta set of functions with shadowing. Now, are there other functions with shadowing? Maybe, but these are some of them. Okay? And so we have a subset of the maps with shadowing that are dense, that is a dense G delta. So in a very, very real topological sense, most maps on the dendrite D have the shadowing property. All right, so we've got a few minutes left. Where can we go from here? Well, with a little bit of extra work, we can actually show that D is, that shadowing is generic in the surjections on the dendrite. There's really only one additional step, and that is to take those SIs that we built. So I'll draw this here. Right, we built these SIs, I guess we did them in red. Okay, we had these trees SI. We took all these TIJs, TIJ1, TIJ2, TIJ3. And all we're going to do is we're going to take one more T, let's call it Ti, comma 0, since we're not using 0. We map all of these as before, so those map across their appropriate SJ1, SJ2, SJ3. And this guy, we map it across so that it covers the image of UI closure. Okay. So the image of UI closure is a dendrite. A dendrite is a piano continua. A piano continua can be covered by a map on the arc, and this is it. Okay. So we can accomplish surjectivity by adding that extra thing. Then that family Rn, or the related family, would consist only of surjective maps, and there we have it. Right? So if we want to push this a little bit further, we have to think a little bit more. So I don't have nearly enough time to get as far as I'd like to on this, but this is leading up to some very, very, very cutting edge results. What if we want to push this beyond dendrites? Okay, so what if we want to go further? Well, a huge part of the construction we did here depended on the unique arcwise connectedness of the dendrite. And if we go beyond that, branch manifolds of higher dimensions certainly aren't uniquely arcwise connected. So this is bad news there. Okay. But we can deal with manifolds because we can control boundaries of neighborhoods pretty well. So we can still accomplish a lot of things. Right? We can sort of map a ball in such a way that it contains some things, and that can be made to work. Can we modify these assumptions? So a result very recently that I've been working on, and it's under revision at the moment, concerns a generalization of the notion of a dendrite. All right, so I have about 10 minutes here, so we're just going to get started on this. So if you dig back into the history of continuum theory, there's two competing things. They're called dendroids and dendrites. If you read Nadler's continuum theory book, we see that a dendroid is defined to be an arcwise connected, hereditarily unicoherent continuum. Okay. This is because of hereditarily unicoherent. Hereditarily unicoherent, for those not familiar, this means that if A and B are connected subsets of D, then A intersect B is empty or connected. Okay. And because of that, this really quickly implies this unique arcwise connectedness. Okay, so that's a dendroid. A dendroid is a uniquely arcwise connected, hereditarily unicoherent, arcwise connected continuum. Not locally connected, or not necessarily. Okay. And then a dendrite is then just a locally connected dendroid. Okay. So this is standard definitions. If you go back to the 1960s, Knaster proposed an alternative definition of a dendroid. We'll put an asterisk by it. A dendroid star is a continuum D such that for any epsilon, there is a tree subset of D and a retraction D to T, which is an epsilon map. So an epsilon map here means that the pre-image of any point has diameter less than epsilon. Okay. So that's a dendroid. These are things that sort of project or retract onto trees in a nice way. Then a dendrite we might define with an asterisk to be a locally connected dendroid. Okay. So these are locally connected continua that retract onto trees. And this right here, this retraction, is actually all that we used in our proof. Right? That was the real property we used. We used uniquely arcwise connected because it was convenient, but the real property that really drove the proof was the existence of this retraction. It's what generated the covers that we needed to make things go forward. All right, now an interesting fact about these two definitions of dendroids and that we have, the sort of standard one and the Knaster one, is that it is an open question, at least as far as I'm aware, as to whether those two are equivalent. And that's actually a very interesting topic. There's a lot of work on it. As far as I'm aware, there's still no answer to that. But what we can see pretty immediately is that every dendrite in the standard sense is a dendrite in this sense. And that underlying graph structure is what really drove the proof that we outlined. So the idea and the object that I work with in my most recent paper, which it's on the archive, it's called Genericity of Shadowing in One Dimension. Should be published shortly after a few more revisions. We can look at a wider class of spaces. So what we're going to do here is we're going to take this notion here for dendroid and we're going to replace tree T with just a finite graph. We're going to allow cyclicity. We're going to allow cycles. All right. So I've defined this should say graphoid. A graphoid, this is something I have defined, a class that I've defined. A graphoid is a continuum X such that for every epsilon, there's a graph subset of X and a retraction, which is an epsilon map. And a graphoid is a locally connected graphoid. Okay? So the graphites here are generalization of dendrites. Every dendrite is a graphite. There are graphites which are not dendrites. With a little bit of work, we can show things like the Menger curve or the Sierpinski carpet, Sierpinski gasket. These are graphites. With a little bit of extra work, we can show that the Julia set of a hyperbolic polynomial with, if the Julia set's connected, is a graphite. So we see this is a significantly larger class of things. And so a theorem is that if X is a graphite, then shadowing is a generic property in C of X and S of X. Okay. And the proof is really not so dissimilar from what we just outlined. The outlined proof there, we did use unique arcwise connectedness, but we could reflavor it in terms of these retractions without too much difficulty. The real difference here and the real catch here is that the existence of nice covers is a significantly deeper and more difficult question to address here. And it's really the only barrier to generalizing things. Okay? Since graphites have graphs as subsets, the best we can hope for is that the nerve of the cover is a graph. Okay? And tautness is a little bit not quite enough because those cores could still be empty. We can end up with something kind of goofy where we have an open set that looks like this, an open set that looks like this, and an open set that looks like, let's see if I can draw this right, something like that. All three of these intersect each other. Their closures meet, so it's taught by that definition. But
Jonathan?
Yeah.
There is a question in the chat.
Okay.
Gerardo asked, how about local graph types distinct to S1?
Say again?
How about local graph types distinct to S1?
Okay, so if the graph is different from S1?
Yeah.
Right, so if the graph is different from S1, you can still have this as a problem because your graph might contain that. And you can run into some weird issues there. And because we want these things to be connected open sets in our construction, we have to be really, 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 really careful. So tautness gets a little weird because of 3 cycles. And if we want to ensure that we have connected open sets, there's this interplay back and forth. We can easily come up with a cover by connected sets, but we don't know what its nerve might be. Its nerve might have 3 cycles. We don't know that. And then if we try to fix those 3 cycles, we might have broken connectivity. So we have to play back and forth. Okay? And it turns out we can do this with a little bit of work. And I don't have a ton of time, but I can sketch a quick idea of how this might work. So the idea here, maybe if I have time, is that we have, I'm not going to draw our graphite. Maybe the graph that we want to map onto is something relatively simple like this. Okay, so this is the graph G that we retract onto. So we can easily cover G, like we did with the dendrite earlier. We can cover G with connected open sets easily enough. And we can do this with whatever mesh we like so that things are nice. We'll stop there. All right. Now, if we look at what our space X does in here, the images of this X here, we might have things in here that look like, this might be something like this. We don't have this, we have all these sort of crazy things going on here. And so the sort of this red, this guy right here, this is the one I'm focusing on. If we look at X intersected with that, we see that it has several components, if I've drawn it correctly, which I didn't. But the idea being that it will have at most finitely many components, and we can kind of take local small bits here. We can cover this bit here, this bit here, this bit here, and we can take that and modify that in a way that we get the desired connectivity, the desired tautness, and the desired non-trivial core. There are a lot of details to that. Like I said, that's available on the archive. I'm going to put an updated version of it up very shortly, which has a lot more details on that. But I will leave it there because I am out of time. So thank you all for being here. Thank you all for your attention. Thank you all for your questions. I will open it up to you guys for questions. And hopefully I can actually see the chat now.
¿Hay preguntas?
Uh-oh.
Let me see the chat.
Okay. My Zoom is freezing up. Can you hear me, Leo?
Yes, I can hear you, but I cannot hear anybody else. So.
Huh.
Is it possible to extend this to other kind of shadowing, like orbital shadowing or these things?
Though that is a really great question, and I don't have an answer for that. I do have that as a question that's I removed from this presentation for the sake of time. But that's actually a really interesting question that I don't have any answer to one way or the other. It's definitely something that is worth considering. I think the biggest issue that's going to come up is that there's not this tight connection between the pattern phi and your pseudo orbits. If you look at something like thick shadowing, you lose some of that connection. And then if you look at something like asymptotic shadowing, you have to almost work with a sequence of covers rather than a fixed one. Something like orbital shadowing is an odd duck in the sense that orbital shadowing deals with these things as sets rather than sequences. And that one, I really don't have a good feel for whether similar techniques would work for, simply because it is so much stranger.
Okay, yeah. Oh. ¿No hay más preguntas, chicos? Cannot see them. Bueno, pues, Jonathan, thank you very much for this mini course. We enjoy it. Hopefully.
My pleasure.
Sorry?
It's been my pleasure.
Yeah, let me see. There are some comments. Yeah. Well, I was saying thank you very much for the course. Hopefully next year we can do it in person.
Yeah, that would be great. I would really like doing that.
Somewhere in Mexico. And it's usually here in Mexico to give a certificate of this. So I will send you by email.
Okay, sounds great.
Yeah, let me see. It seems there is Shadowing for Dummies, which is the book for Shadowing for Dummies.
Right.
Well,
sounds great. Well, thanks so much for having me.
Yeah, thank you very much, and well, see you next time.
Take care, everyone. Thank you so much.
Thank you. Bye. Chicos, tenemos un descanso de